Tom has a long history as an engineer and also as a manager with Cisco. He's a Cisco fellow. And what's really distinguishing about Tom is the fact that he's been a successful serial entrepreneur, co-founding Adiamo and Crescendo Communications, and I believe Crescendo was the first acquisition for Cisco. Tom?
I want to talk to you a little bit today about data centers and a little bit about how I see them evolving, and I think a lot of this is not going to be new to you. What I hope to do, though, is make you think about them sort of in a little more focused fashion and some of the problems that might be facing in the future, and hopefully can inspire some solutions in some of these areas. And so here's the data center of the future. Oh, wait a second. I guess this is the way data centers used to be designed, I guess. So this is sort of the classical architecture you might pull off of the web likely from Cisco, showing how we have designed data centers in the past. And there are a number of problems with this architecture. The first thing is it's obviously quite complicated, complex. There's a lot of hierarchy on this. With so much hierarchy, you can imagine I might have a lot of choke points up in the core of that network. I've got a bunch of cross links between switches. It's ultimately not a particularly scalable solution. It's not particularly predictable in terms of bandwidth, but it has served us quite well for many years. One thing I want you to think about is that most of the networks out there today look like that. Now, a lot of you are in the data center space and working on software-defined networks, and we're all thinking a different kind of topology, and myself as well. And sometimes we think that that's the way the world is, but it's not. The world actually looks like this thing here. So one of the challenges is to figure out how to transition out of this into something that's a little more appropriate. So what is more appropriate? Well, what we need to do is borrow from the world of compute. And the world of compute has gone to scale out rather than scale up. The model here is a scale-up model. We need to go to a model which is a scale-out model. We also have to recognize that the nature of traffic in the data center is very different today than it was in the era of this topology. The traffic in the data center today is 75% or more is server to server, east-west kind of traffic. It's machines talking to other machines. And that traffic has a completely different characteristic than the traffic that would be from client to a server, or to an end user, or to a server. There may be hundreds, maybe thousands of messages that are exchanged in order to accomplish something. So the latency of this network becomes much more important, because it's not the latency of any one path is particularly important, but if you multiply it by 100 or multiply it by 1,000, it becomes a big impact. The sort of the distribution of flow sizes is likely to be a little bit different. When you are exchanging lock messages or doing clustering across one of these networks, your flow sizes are going to, a lot of them are going to be really small, but you're also going to be moving a lot of big data. So you're going to see a big spread in the size of the flows that are occurring in this data center. And we have to be thinking about how do those flow sizes interact with one another. How do the big flows impact the small, and how do the small impact the big? Or is there a problem there at all? One thing that I like to think about is if you drop a packet and you happen to drop a packet in a small flow, it's going to have a big impact. You drop it in a large flow, it's not going to have a big impact. And so maybe we should be treating these kinds of things differently. And so the topology that we all know we're headed toward is the fat tree, or the cloth, or the multi-rooted tree kind of a network. And so this I'm showing here a 2-tier with a leaf and a spine, but clearly they can go to more tiers than that. Now there are other topologies that are a little more experimental. may have some advantages in terms of their behavior, in terms of oversubscription. Maybe you can build larger networks with fewer links, all of those kinds of things. However, this, I believe, is going to be the most pragmatic, the most practical. And the reason for that is we have to remember that there are people that are connecting this thing up, and they're building this network. And if I have to have a spreadsheet, or I have to have a calculator to figure out what links goes where, it's not going to work particularly well for the union guy who is deploying these networks. And so this topology is good enough for the kinds of things we want to do. And I think it's actually quite good for the kinds of things that we want to do in data centers today. It has as much cross-sectional bandwidth as we want, although networks are typically oversubscribed. It can have a network diameter as big as we want, although they tend to be bounded on some sort of administrative boundary and what people can deal with. And so we think this is going to be the topology of choice moving forward and away from that multi-tiered one I showed earlier. So now looking at this, Mohammed spoke earlier today about what are the link speeds in a network such as this, and thinking that, you know, if the access links are at 10 gig, then maybe the core links need to be 40 gig or more. And I'd like to present a little bit of data that might back that up a little more. If we take a look at the data center Ethernet ports and the volumes of these ports today in the market, we can see that the 1 gigabit Ethernet has now dropped below that of 10 gigabit Ethernet. And what's driving that? Well, if I look a little bit deeper into this and look what's happening at the server itself, the server is still predominantly at 10 gig. And in fact, servers today are still a little bit more of 1 gig versus the 10 gig. And that's clearly, that transition is happening very, very quickly. And so what we see from that is, the takeaway from that is, in this network, these edge links are rapidly becoming 10 gig. So what's going to happen in the core? Well, we see a rise of 40 gigabit Ethernet coming in the starting basically this year and coming into the next few years. And 100 gigabit Ethernet really isn't doing much. Okay, so that's telling us that we're starting to see that 40 gig being deployed in the core of that network. And if we look at the price, or the cost, or the price of bandwidth in these networks, we see some interesting trends as well. And what I'm showing here is the cost per port of Ethernet, and I've normalized it to 10 gig. So a 10 gig Ethernet port has a cost of 1. And we can compare that to 1 gigabit Ethernet. And you can see that the 1 gigabit is much more expensive than the 10 gigabit if you want to deploy 10 gig worth of bandwidth, or 100 gig or some amount. Clearly, if you want to deploy less than 10 gig worth of bandwidth, it's going to be cheaper to go with the 1 gig. The 40 gig is almost the same today as the 10 gig. And in 2 years, it in fact will be the same. The 100 gig, on the other hand, is still quite a bit more expensive and will continue to be quite a bit more expensive. And if we look at modular switches, we see, in fact, that already 40 gig is less expensive than 10 gig for a given amount of bandwidth. And that pricing trend will continue moving forward. And yet the 100 gig is still twice as expensive as 40 gig in terms of interconnect. And so all of this is telling us that really 40 gig is going to be the interconnect of choice moving forward. And so if we take a look at this network, what we want to do is kind of beef up those internal links. And so when we build this. Now, that has the positive impact where, again, Mohammed was explaining, when you're going from smaller link speeds into faster link speeds, there's a statistical advantage in how you're going to be able to distribute your flows. However, the ratio of 1 to 4 is not a particularly comforting and big margin. It's not a lot of space in there. And traditionally, we've had a ratio of 1 to 10, because Ethernet has always gone up in orders of magnitude increments. And here we're going to 40 gig, which sort of feels like a half step. And so I anticipate that we're going to see a lot of work about how to place those flows in a way that avoids congestion that might occur in these networks. So I think quite a bit of work needs to be done in that area. Okay, so what else do we need in this network? Well, we need to connect something to it. And there's a variety of things that are going to be connecting into this network. We have physical servers, we have virtual servers, storage, services, we have the connection to the outside, MAN, WAN interfaces, other parts of the data center perhaps, campus, all of these things. Notice that they connect at the edge of the network. They don't connect up into the core. And we think that's going to be important because if they connect into the core, they're going to create hotspots. And we really want the traffic to be distributed across those core switches as evenly as possible. And if I have an external router connected into one of those spine switches, all of that external traffic is going to be directed to that one spine switch or two spine switches or whatever it is. Now, if you took that router that you're going to connect to the outside and connect to all four of those spines, or in my example, or however many spine switches you have, well, that would be fine. I wouldn't have hotspots. But at that point, just fold it down and it looks just like one of the leaf devices here. So it's back again to this topology. And then, of course, another requirement that we have coming into this data center is IP anywhere or IP mobility, workload anywhere. And this is the idea of an IP address doesn't have to be bound to a particular location. And historically, this has been what has happened because we've always kept an IP address within a VLAN. Because if it's going to move, you are keeping the same IP address, therefore you must have the same subnet, and an IP address or a subnet and a VLAN are bound together one-to-one. Well, we're finding out that that in fact doesn't have to be the case. And that yes, an IP address does have to move, but you could deploy that VLAN sort of instantaneously where that IP address appears. And maybe you won't call it a VLAN, maybe you'll call it something else, a bridge domain, or maybe you'll route right at that first switch, and so you don't have VLANs at all, or sort of get link locality of those things. But to facilitate the movement of these IP addresses, we go to overlay networks, and that's how we're going to be virtualizing the network. And we see that across the industry. Everybody's talking about overlays. Not that many are actually deployed today. But it solves a problem that we've been grappling with for a long time. And this is the problem that the IP address has two functions in networking today. One function is it tells you where you are. It's your address, just like the address on an envelope. And that's been sort of the classical thinking of it. But it also tells you who you are. And because we've convoluted those two concepts in the IP address, it's been very difficult to separate them. And so what we want to do in these data centers is be able to decouple your identity from your location. So it's location identity split. A lot of protocols out there to address that. In the end, I don't think what protocol you use to make that separation is particularly important. The important thing is we have that separation. And so we see these networks being completely virtualized. But now when we talk about the virtualization of the services down here and virtualization of the servers, do you have any idea how much virtualization occurs? How many servers, what percentage of the servers are virtualized? Anybody have an idea? Yes? 80% virtualized? That sounds like a pretty good number. That was, my feeling was more 50%, 20%. Yeah, so if we take a look at Gartner, 21% of the servers are virtualized. And I look at that number and it's like, okay, sounds kind of funny. It didn't sound right, right? And these guys aren't necessarily genius. They're pretty smart, but they could be wrong. So does it make sense, that number? So taking a look at that number, so well, let's look into it a little bit deeper. And we can look at some other things that have been published about this. Pat Gelsinger noticed that 50 to 60% of the workloads are virtualized. Pat Gelsinger runs VMware. Okay, so he should know. Okay, but that's workloads that are virtualized. 6 out of 10 workloads are running in virtual machines. Okay, so it's consistent with the previous quote. We have the total virtual OS instances will be 70% of all of the OSs that are out there. And it's going to reach as high as 82%. So that kind of jives with the numbers we're thinking about. But let's not confuse virtualized OS instances with physical servers. And in fact, if we think about that 20% number, and I take 5 servers here, and I virtualize 20% of them, so one of them is virtualized. And you know, how many virtual machines are we going to run there? Let's pick a number. I'm going to pick 10 because it's an easy number, nice round. And it seems like that's a pretty common number. We hear numbers as high as 100 and as low as just a couple. But if we go with 10, and then I take some workloads and I distribute those workloads out onto those operating systems, I'm going to put 10 workloads on that first server, and then I'm going to distribute the other workloads across the remaining servers. And we do the math, 70%. And so it really probably is correct that 20% of the servers, so somehow Christos happened to know the answer at 20%. And so that's an interesting fact. When we think about virtualization happening everywhere and being done so pervasively, maybe it isn't quite as pervasive as we think. The numbers are construed in a certain way. And now imagine that this hypervisor, in fact, had 100 workloads. I would have to have a whole lot of servers out here to bring that percentage down to 70%, right? I would have to have, I don't know, would probably have to have another 40 servers out here. And so, if anything, the percentage of servers is even lower than that 20%. In fact, if you look at the quote in more detail about the amount that's virtualized, 2012 was 14%, and it'll reach 21% in 2016. And so maybe the number is more the 10 to 15. And so that raises a number of challenges when we look at our network and what we need to achieve with our network, is that we have to assume that it's going to be a mixed environment. And how do we address that mixed environment? And there's a lot of solutions out there for doing that. But I think there could be a lot more progress made in that area. You know, we go through proxy agents, there's virtualization done in hardware, there's a bunch of different solutions to this. But it's going to be a fact of life in these data centers. Now, there's one thing that I've missed in this data center. Does anybody know what it is? It's the most important thing. Right? Bandwidth capacity, it's not my answer, no. Cooling. That might be. No. The most important thing in the data center. What is the most important thing? Two most important things in the data center. Management, security, no. What's that? Uptime, no. It's more obvious than that. Well, you're pretty close. No, applications. The other most important thing is data. Everything else goes to support those things. Right? If we didn't have applications, we wouldn't bother to build a network. We wouldn't build a data center. What's the point of having it if you're not going to have information in that data center? And so we have to be thinking about applications. Okay? And it's an interesting thing, if you think about networking today, the language we use to talk about applications, or talk about the data center, excuse me, has nothing to do with applications. What terms do we use? We use subnets. We use routing, bridging, IP addresses. I'm just saying all this, you have no idea what application I'm talking about or the structure of the application based upon that information. So we need to start thinking more about what is running on this data center rather than, or what its purpose is and what it's for, rather than the mechanics of how it's being used. And I think that's been something that has been missing a lot in the industry in general. So keeping that in mind, I'd like to say a few words about all of these. So first, this application focus. Because we haven't been thinking about applications, we spend a lot of time in networks, at least historically, thinking about fairness. Well, fairness basically saying, since I don't know anything about the applications, I'm going to treat everything fairly. Well, maybe that's not the right answer. I may have some applications that are more important than others. Okay, well, you have quality of service. Well, the quality of service implementations have not been particularly successful. They work, they're just not widely deployed. If I have to debug something in the network, I would like to understand where in the network I need to be focused on. Imagine this data center has 100,000 servers, and instance 38 of my web servers, of my e-commerce application, is having a problem. The first question you're going to get is, where is it? And how do we facilitate finding these things? How can we contextualize the information about the network so we know where things are? So if there's a failure, a link failure, what are the applications that are going to be impacted by that? So everything we do in these data centers, we should be asking ourselves, well, how does that relate to an application? Because the application is the most important thing. Okay? And I wrap applications and data together in this. Okay? So really have to think about that application focus. When we talk about performance in data centers, we talk about, and I think it was mentioned here, bandwidth or latency or throughput. All of these things are terms we use in networking to talk about performance. Applications don't care about bandwidth, latency, and all of those things. What they care about, did the data get there, and did it get there quickly? And I'm not talking about packets. I'm talking about objects or messages. Okay, so that's something that Mohammed was using in some of his presentation, was looking at flow completion time. Flow completion time is pretty close to what we think about as application performance, right? Because it encompasses not only latency and throughput, it also packet drops and efficiency of the protocol stacks. All of these things, everything is going to impact the application getting data from one point to another. So I'd like all of us to focus on flow completion time and not these other things that are not nearly as important. Complexity. So complexity is moving. And what I mean by this is the network that I showed you on that first slide was a very complex network, and it's got all kinds of protocols running in it, and it's got spanning tree here and there, and you're doing routing at certain layers and not at other layers, and redirecting, encapsulating, and doing all these very, very complicated things. And by the way, there's 25 different ways to calculate a topology, and your mileage will vary. Okay? I think we're moving away from that. I think we're going to be down to just a couple of protocols. We're going to be simplifying this topology, so it's just a one tier or two tier. Just simplify, simplify, simplify. We're going to standardize on a lot of sort of the baseline down at the physical infrastructure. And yet we're going to add complexity in other places. As we become much more virtualized and abstraction hides the details. That's going to add some complexity. As we have an elastic data center where things are expanding and contracting and moving about, that adds a huge amount of complexity. When I have to go to debug something, an application in a data center, and I go look at it, and just as I look at it, it moves, that's clearly going to be kind of a problem, right? So we need a whole new set of tools to deal with this. Everybody hates spanning tree. I talked to, before I left Cisco, I was working at a lot on some multipathing stuff, and I say, oh, well, we're not going to run spanning tree, and I would get applause. Because you get applause. I never get applause. I get applause for not running a protocol. But there was something pretty nice about spanning tree, is that I could tell you where the data went, what links it went on, because there was only one choice. And so when you actually had to debug a problem, and nobody likes to talk about the debugging problem, when you had to debug it, you kind of knew what to do. You go to the link and you'd put a sniffer on it, and you'd grab the packets and you'd be done. In a highly multipath environment, I don't know where to look for the data. Well, I do. I have to look everywhere. How do I look everywhere? The cross-sectional bandwidth of these things is petabytes per second. I can't dump it to a sniffer. It's not practical. So I need to have tools and new techniques of how to debug these systems. And unfortunately, I think a lot of those tools are going to constrain the topology so that I can debug it. But of course, we all know what's going to happen. When I constrain the topology, the problem's going to go away. And those are the problems that are going to be more difficult to deal with. So how do we do forensic analysis? How do we debug, troubleshoot these networks? And I think not enough energy is being put there. One example of this that I like to use, and there's a bunch of people that have been in my group at one point or another in this audience, and they've heard me say this. There's a feature in Cisco switches called SPAN, Switch Port Analyzer. We put it into the Catalyst 5000 in the mid-90s and came up with this feature. It's the dumbest feature, okay? It basically says, send all the data that's going out there, send it there as well. It is one of the most important features of these switches. Now, clearly, forwarding packets properly is the most important, but sometimes these stupid little debugging features become critical in a lot of places. And we need that kind of thing. Unfortunately, I don't know how to span an entire mesh network all at once, or even how to collect it. So we could use a lot of research in that area. You know, streaming analysis, those kinds of things can add a lot here. Scale. So we can see that we can achieve a lot of scale with this topology, and that's all good and fine. That's a sort of a physical layer scaling. Of course, the next thing is, well, what about the data plane and address scaling and those kinds of things? And with overlays, you know what? I think we've got pretty good scale. And you look at an IP address with the summarization, it's got fantastic scale. But what about control planes? And we see a lot of work happening in this area, and it's a big revolution in the industry these days with the SDN controllers, software-defined networks, and rethinking the whole controller aspect. And you know, maybe if we took a different look at the network and thought about it differently, and certainly having more simple topologies is going to make that easier. Having more regular topologies is going to make that a lot easier. But those solutions face a lot of problems as well. We have a shared fate problem where the controller is separate from the data plane, so we're directing things from a distance. Well, what if that connection is somehow lost, or one end or the other is not functioning properly and the other end isn't able to detect it? I think these problems will be overcome, but there's a lot of work that still needs to be done there before they can become really production-worthy networks. And then that controller in of itself needs to scale. You know, there's clustering that has to happen. Well, it's a challenging task. And you have to do that while at the same time providing a rich feature set, because there are a lot of things that applications and customers have become dependent upon or used to, that they like, that they're going to want to see in these environments. But scale is something that's going to have to be addressed. And the other part of scale is management. So, you know, you get a control plane, fine. Do you have any idea how many servers typically an admin will support? I'm not talking about the Googles and Facebooks of the world. I'm talking about everybody else. The smaller data centers, the enterprise data centers. Any guesses on that? You say how many? 10, 20 servers. Anybody else? 50. He's a brilliant guy. He said, yeah, it's about right. It's anywhere from about 20 to 100 servers per administrator. Yeah, how does he know all the answers? He's been looking at my notes. Okay, fine. Do you have any idea, Christos, what it is for a massively scalable data center like a Facebook, Google, or Microsoft, or somebody like Yahoo? Any I suggest? His answer was between 2,000 and 10,000. I think it's at the high end of that. It's, you know, more 10, and I've heard as much as 20,000. Wow, that's a big gap. Why does that gap exist? Well, of course, you know, if you're Facebook, you run one application, Facebook. Okay, that simplifies things. You have an army of people that can write software to automate things, and I don't know if that gets counted as admins or not. It's probably, so there's probably funny business with the numbers a little bit. That helps. So how do we enable and how do we empower those smaller enterprises to get that kind of scale? And by the way, you also have a social impact, or a psychological impact, or I don't know what the right term is. I was trying to think of this on my feet. If I'm going to go in and say, okay, you know, you guys, you're the network administrators, I've got this great solution. Oh, by the way, 90% of you are going to be fired. So let's embrace it. And so you can imagine how that conversation might go. And so there is a suspicion. And we saw this when when Cisco introduced IP telephony. The telephony guys did not like it at all. They didn't want to have anything to do with us, wouldn't talk to us, started to play games like, oh, well, you know, we're responsible for procuring the telephony equipment, and we don't have you on our approved vendor list, so therefore we can't buy Cisco equipment to do telephony. It's like, okay, you know, that's clearly a bureaucratic excuse, but they were concerned about their jobs. And so while we do have to get to that 1,000 to 1 ratio, maybe we don't have to get to 10,000, but it should be a lot better than 10 or 100 to 1. There is going to be some resistance from the buying centers of these companies to that. However, if you talk to the CIO, it's going to be all thumbs up. So there are ways around these things. Performance. So as I mentioned before, I think performance needs to be thought about in terms of application performance, not performance of the network. I don't want to hear about performance of the network. I don't care what the network performance is. What I care about is application performance. As Paul was saying just a few minutes ago to me before this, he says, well, it's not about doing storage, or it's not about doing networks or doing servers. You got to do the whole thing. And I think application is really encompasses that, because an application is dependent upon the CPUs, it's dependent upon the network, and it's dependent upon the underlying storage. And we have to think about all of these things together. From a network perspective, I think that component, as I said, is going to be about flow completion times. It's going to be one of the prime metrics. But it's not going to be the only one. I think that there are going to be cases where you're going to want to make guarantees. It's not necessarily I want to be the fastest. I want to make sure that I can complete within a certain window. I don't have to be any better than that. So sort of deadline scheduling, some of these ideas that we've seen in the industry, I think are going to be important. There will be a place for making latency guarantees. There will be a place for making bandwidth guarantees. But for the bulk of the time, it's going to be, let's optimize around this flow completion time, or ultimately optimize around application completion time. Now, one of the problems that we've always had is the networking guys don't know what the applications are. So as I said before, we're going to reduce latency, reduce bandwidth, and we're going to be fair to everybody. And the application guys are like, well, I don't know what network I'm going to go on, so I'm just going to assume this sort of dumb pipe, and I'm just going to move packets back and forth, or move messages back and forth. And as long as it delivers my message, I'm good to go. Well, I think there's a huge opportunity if we can somehow cross that gap. Somebody is going to have to take an application and optimize it for a network, or for a class of networks, for a set of networks. And these SDN controllers are promising this, but haven't seen it. But at least they have a promise. Okay? Where there are northbound APIs, which I think is the important part about these controllers, is not the southbound. OpenFlow I could care less. What I care about is the northbound, what's happening above there, where it interfaces with the application. That's what matters. And if you can cross that boundary, can we do something in these applications to make them run? Can we do something to make Oracle run faster on this network than it would otherwise? That may mean not being fair in the network. It may mean dropping more than you would normally want to drop. It may mean who knows what. I'm making that up. I don't know what it means. But let's think about performance in those terms. And we have to have good performance. But to get those good performance, we also have to recognize that in the end, you are going to need an infrastructure that can run a lot of packets really fast. You're going to need the 10 gig interfaces, the 40 gig interfaces, the 100 gig interfaces. We can't ignore the sort of table stakes of networking as we move forward, but always as that goes to apply toward applications. Operations. Operations to me is maintenance, troubleshooting, and debugging, or as you want to call it. And expansion, contraction of the network. We show a fat tree topology here. How do I make it bigger while it's running? Okay, well, great, plug in some more switches. At some point, I run out of ports in that core switch. How do I expand that in a way that's not disruptive? Kind of challenging, right? We already talked about, actually more on the maintenance side thing. Ultimately, there's a lot of switches. There are going to be soft switches. There's hardware switches. There are controllers. All of this stuff. Well, now I got to do a firmware upgrade. Okay. How do I pull that off? I've got to do that in a way that's going to be non-disruptive. I can't take down any of my applications. By the way, that's one of the things that these networks, of course, we all know, is 24/7. There is no scheduled downtime. How do we handle all of these things? How do you orchestrate that across this entire data center, not just across the network? Troubleshooting, we talked about that a little bit already, but as a span. But what are the tools that need to be invented to make it so we can debug these networks? So I mentioned span, but what are today or yesterday, really still today, what do you think is the two most important tools for debugging a network? Any suggestions? Ping, I heard ping and trace route. Really? Come on. I mean, that's pretty lame, right? And by the way, those don't work very well in multipathing networks. But that's the bread and butter of today, debugging a network. We've got to come up with sort of those fundamental go-to, baseline infrastructure tools so I can figure out what's going on in this network. Give me a multipath aware trace route. So when I do a trace route, I see all the paths. At least do that. Something in ping that can probe all of the available connections. Oh shoot! Now I have any cast address, so I do a ping. I need to ping to all of the instances. How is that going to work in one of these systems? A lot has to be done in that area, and we will for sure do a bunch in terms of network management and gathering statistics and all of those things that networks have always done. But those we've had that forever, and they're not the most important features. The most important tools. The most important tools are still this ping and trace route that have been there forever, and they're dumb, but dumb like the span. So maintenance, troubleshooting, debugging, and then how do you evolve this network? One thing in this that we hear quite often from our customer base, I keep on saying I'm thinking Cisco. I've been at Cisco for 20 years. It's hard for me to get out of that mode, and I'm in a Cisco building. The number of links that are failed is about 1% all the time. There's always some link someplace. So if you have a small data center, maybe you don't have any links. You have a large data center, there's always some that have failed. How do we deal with that? Let's assume that links are down. Are our algorithms for balancing traffic in the network, are they sufficient? Do they handle these kinds of failures in a systemic way? Can we detect them? Can we find these failures? Let's consider in the massive networks, there's always something that's going to go wrong. And that's all part of operations. Security, the toughest question. And a few people, I think, suggested it was the most important thing in a network. So maybe it's the second thing right after applications. It's also the most ignored thing. If you look at an IETF draft, typically in the end, they kind of say, well, security considerations left for later work or something like that. And it's like, okay, yeah, good. I've certainly told a number of customers, dealing with security or making your network more secure will not make your life easier. You don't do it because you want to. It's not going to save you money. Okay? Well, it might in the bigger picture of things, but and it's extremely challenging. And it's not just about encryption. It's not just about authenticating the user. It's all about these attacks, and of course, it's always escalating and always changing. The being able to do an analysis not only of what the attack was and where it was, but assuming that it happened, how much information did they get? You know, where did that information go? It's that forensic analysis to understand how are you going to do damage control. Because you don't necessarily want to send a letter to all of your customers. You only want to send a letter to some of your customers, right? If you have a data center that's been compromised. And how do we deal with these things? Another problem we see is it used to be that you had, you know, a bunch of computers were used to attack another computer. Well, now, because of cloud services, you get data centers attacking data centers. Okay? It's a whole other scale. Or you can be attacked from within because, guess what? I can get an instance on the Amazon cloud, and I can attack other customers of Amazon from inside of Amazon. And they don't want to stop me from being their customers, right? They don't know the difference. And so it's a whole new paradigm when it comes to what can be done in terms of these attacks. If I need 500 computers, I can just put my credit card and I get 500 computers. I don't have to compromise anything. They just give me the computers. And then I the stolen credit card, when I'm done, I just walk away. And so we have a whole new class of things that are going to be going on in these networks. How do you deal with them? How do you detect the bad guy versus the guy who's just got hot content? Not eye contact, but hot content. And so security, it's the easiest thing to ignore. It's the thing we least like to deal with. And unfortunately, it's also one of the things that the end customers least like to talk about. They don't want to admit that they've had a problem. But most customers that I've talked about, if there's a little bit of a whisper in the hallway, is, yeah, we've been attacked. Yes, we've had some problems. But you know, we can't publicly say anything about it. And so we have to continue to work on security, and I think it's even more important today than it ever has been before. Last point is about the approach to all of this. I think that what happens too often in the industry, especially as the industry is changing, is that we become very polarized. And they say, well, you know, this is the way it has to be done. Or that's, you know, we have to do it all software, or we have to do it all hardware, or we have to custom silicon, we have to do merchant silicon, we have to do this, we have to do that. And my experience has been that anytime you have sort of this spectrum, the right answer is typically not at one end or the other of the spectrum. It's someplace in between. That there are advantages of both ends of that spectrum, and the best solution is going to encompass some sort of compromise, and I don't mean compromise in an, oh shoot, I gave up a thing, but a compromise in terms of I can see that maybe it's a better way to do some of these things with your technique than it is with my technique. Okay? And that together can build a better solution. And so I'm concerned that there are a lot of assumptions that are built into how people are solving problems, assumptions about, oh, you know, this can't be done, or this shouldn't be done, or this is a better way, or that's a better way. And those assumptions kind of limit the solution space that we go after. And I know I'm being a bit vague about this, but it's something I think we can all relate to at a certain, with any kind of problems that we solve, that it's better to have a balanced approach to any of these. So that's what I wanted to say about data centers. Do we have any questions? No questions. Put you all to sleep. There's a question in the back. Go ahead.
I don't think that there are anybody in the audience who would disagree with the points that you mentioned as far as their significance and the presence of the problems, the severity of those, and what we need to do. But in your experience, why is it that when we go back, we only go after the segment or the area that we like and we are comfortable, even though we know that that may not be the most important area, but we end up just making a faster link or more ports in the switch, or switching from whatever interface to whatever other interface and so on. But we essentially ignore the things that has been around for quite some time. And based on the comments that you made, it is unlikely that this is going to change, at least in the near future.
So the reason is because we're humans, and we tend to go to our comfort zones in general. And I think that's ultimately the fundamental answer to your question. You know, I think in the industry in general, we have an installed base, and we have the new ideas, and you can't just come up with something that says, okay, I'm going to redesign the internet. Right? It's just not going to happen. I mean, there's lots of suggestions on how to do that, and everybody can agree that maybe that's a better way. What we can do is we can evolve the internet. We can evolve the data center. And when you do that evolution, you know, every step doesn't look very different from the previous step. But, you know, my grandmother's Ethernet is completely different than mine. And it really has evolved a lot, if you think about it. You know, the Ethernet was CSMA CD back in the day, right? And we've moved a huge distance from that. You know, and maybe we don't move as fast as we should. But I think it's been a very interesting time in networking in the last couple of years, and there's been a lot of movement. If you look at all of this that's been happening around what Dan has been doing with the Open Networking Forum and Open Flow, and the questions that are coming out of that, I think have, first, they've rocked the industry, and I think there is a lot of acceptance of these ideas. A lot of work before they can become, you know, reality in any kind of important kind of market share thing, but it takes a long time to introduce new technologies. You know, again, speaking from a Cisco perspective, you know, Cisco will have an operating system that's out there in the field. They'll find some bugs, not that, you know, a big surprise to anybody. Fix the bugs. Customer wants it. It might take them 2 years before they'll upgrade. Why? And, you know, the engineers are like, I can't believe I still get a call on this bug. I fixed it 2 years ago. It's crazy. Well, there's a lot of inertia, and there's a lot of conservatism around making these kinds of changes. And people generally have the idea, well, it's not completely broken, so I'm not going to fix it, even though they can see that they're going to get to something much better moving forward. These changes to these kinds of topologies and these ideas, to me, compared to other kinds of changes that happen in the networking industry, has been a flash. It's been incredibly fast. Compared to, you know, how long did it take us to get rid of token ring? And, you know, when we knew all along that wasn't a very good idea. So I don't know if that answers your question, but, you know, it's life. Dan.
I enjoyed your talk, Tom, and I actually took a lot of notes, but you didn't answer the question that I really would like you to answer.
Uh-oh.
So I'm going to ask the question.
Yes.
What is Insieme doing?
What is Insieme doing? Well, you know, we are still stealth mode, and so I can't tell you. Bottom line. Which was one of the challenges I had when Christos contacted me for this talk, and it's like, well, I can't actually talk about anything. I can't talk about what we're doing, and I won't be talking about what we're doing. Let's just say, in general, we're working in the networking space, data center space, and surprise, actually shock in the back of the room. And we think that applications need to be first-class citizens in those data centers. Yeah, I do. Next question.
So I really liked what you said about the application performance. Brings me back to Hennessy and Patterson.
Okay.
But I was wondering what you thought about both today and in the future about the balance between guaranteed network level performance versus average case application performance in terms of, the hero tests that we pass of, 64-byte packets, lookups at,
I get your question. Yeah, so anybody that's designed a switch, you know that you have to be able to run line rate with minimum size packets. And we also know that there's no workload in the world that looks anything like that. So why do we have to, that's a so-called hero test. I think those tests are a disaster. And I've always thought that. However, I've been at the mercy of those tests. They probably increase the cost of the networking infrastructure by 50% or more for something that we will never actually have to switch. But in the end, if the customer is not particularly sophisticated, and you look at a data sheet and say, oh, that one goes to 11. Therefore, I'm going to buy that one. And what can you do with that about that? And it is what it is. I don't know how many of you have kids in high school. And right now, to get into college is this arms race amongst kids, and they've got to do, start orphanages and take AP everything, and to do this crazy stuff. Because, yeah, they have to be, star athletes and straight, a 4.5. It's crazy. And why? Because all the other kids are doing it, and if they don't, they won't get accepted to the college. And so kind of have that same kind of arms race happening in the networking industry. So I don't know how to fix it, but it's been a problem all along.
And the other question I had related to application performance is, given that there are a variety of different applications and that they change over time, do you have any recommendations or ideas about how to develop networking products geared toward application performance?
Yeah, I have some ideas. I think you have to start to think about generalizing behavior that applications expect from the network, or what they're going to do across the network. And I think you could probably generalize how does search work, maybe. Okay, and sort of what does traffic look like, and what would be good for that kind of traffic and not so good for that kind of traffic. Kind of like, as an example, and there's been a lot of work published about this, about better never than late, right? If I'm not going to get the results, I don't even want to consume bandwidth getting it, right? I think you have to start with something like that, and to understand, because if you pick a particular application, your market will be this big, and maybe that's going to be great. Maybe there'll be a niche player that can do that, but that is one of the challenges. I'm not saying that it's an easy problem to solve. What I'm saying is I think there's a lot of potential there.
So coming back to sort of from those and then.
Yes. So you take your application. I'm going to repeat just because for the benefit of those that couldn't hear you. You take your application, break it, understand what it needs from each of the components, and then work on the performance of that component, whether it's storage or network or compute. Yes, you have to take those kinds of approaches to try to generalize a solution as much as you can, so you have the largest available market, yet focused enough that you actually accomplish something that can be meaningful. So, yes?
Well, it seems power is not on your hot list. Could you elaborate why or why not?
So power is part of the table stakes, and maybe I spent too much time on link speeds. We'll have to do terabit links. I didn't talk about them, but that'll come. There are some things that you just have to continue to work on. Power is clearly a big concern. Interestingly, you know, I don't hear about it nearly as much as I did 4 years ago. And it feels like we've kind of gotten through that bubble, but I think it's because the products have had a time to react, and the power consumption is better than it ever has been before. But really, the kinds of things that are going to matter, and I had a bullet in my slide, and I removed it just in the interest of time, is the total cost of ownership is really one of the biggest factors. So it's the cost of the equipment, it's the cost of operating the equipment, and the cost of running the fans and cooling the infrastructure, and all of that is a big part of what is important in these data centers. You know, I think it should be interesting to create a scenario where the small enterprise or the small consumer, not consumer maybe, but small business can be as efficient as an Amazon. And so they have a choice of whether to go to Amazon or to build it themselves, and that clearly would include the power. Good point. If anything, it's an oversight on my part.
So on the topic of application performance, which is a very good point that you raise here, you are a fabric person, and you mentioned application end-to-end performance, but there's no mention of network interface. And I've seen
no mention of what?
Network interfaces, NICs.
Network interface cards, yes.
So based on your years and years of experience, there seems to be this ignorance between the fabric people and the NIC people, and they will say, NIC people will say, I deal with application a lot more than the fabric.
Yeah.
And you want the application to talk to the fabric through SDN, but they talk to the NIC. So why do you think it's the case, and why it's that way?
You know, that's a very interesting question, and I've pondered that question a number of times myself. You know, I think that there is a lot of low-hanging fruit in the network interface cards. If we look at the end-to-end latency across a network, there's a big chunk of it sitting into that adapter card. The behavior of that adapter and its impact on the network in terms of creating burstiness and those kinds of things is pretty significant. You know, in my world of the switches that I've been working on, we actually, Harry Quackenboss, 3 rows back or from you, knows this quite well. At Crescendo, we developed a network interface card, and we, you know, had that was part of the business, but it wasn't particularly profitable business for us. And then we were acquired by Cisco. We ultimately sold it off, and it's always sort of been the assumption that you know, not enough margin, we're not going to do anything with it, and so there's always been sort of a neglect by Cisco, and I can only speak of Cisco in that regard, about the connection that could have happened between the network and the network interface card. Cisco developed the UCS platform, and there is a NIC card there developed for that platform. Is quite capable, and it provides a number of performance benefits, but it's not widely available on the market. And I've always wondered why. And that is not, they didn't ask me, and it's never been my area, so I don't know the answer of why that was never made more widely available. But yes, there is that component, that layer sitting in there that is, I think a lot of improvements can happen. Okay.
So in the spirit of, instead of scaling up, scaling out.
Yes.
And in the spirit of applications becoming important, in the era of network function virtualization, what and when wide area networks start becoming part of the picture?
When do wide area networks?
Yes. How and when wide area networks become part of the same picture, or there's just a border router that takes care of the things?
So, you know, I think you will see them become more and more integrated with the operations that happen in the data center. As we are able to provision multi-tenant environments rapidly, you clearly need to do that, clear out to the WAN interface into a VPN, as an example, and rather than doing it in a two-step process, that will become more and more integrated. Why is it generally left out? It tends to again come from market dynamics. It's two different buying centers developed by, the products are developed typically by different companies, quite often by different companies. And so there isn't that much communication between them. Overlays are going to address quite a lot of that. And also you see companies like Google that are making a lot of progress in this area where they are using their controllers to control the WAN interfaces and seeing a lot of value come out of that. And so I suspect we're going to see more and more customer demand to do that same kind of thing, in which case that will ultimately be put into the products that are in the data center. So that is an area of optimization that will come. When we talk about performance, first we'll talk about performance in the data center, and then we're going to have to talk about performance across data centers. And once you do that, if there's communication that goes across that WAN, you're going to have to make sure that's part of that performance equation. So.
You mentioned that northbound APIs will be very important in the context of application focus.
Yes.
So where should the standardization of these APIs come from? Should they be vendor specific, or should they be standardized by the networking industry or the applications or operating systems? Where do you see the standardization coming?
So great question. I don't think we know yet. Mm-hmm. I had the opportunity to lecture in a course at Stanford, and we used the OpenFlow controller as doing some experiments. And from one year to the next, the APIs that were used went from C++ to a Java, and I'm sure it's something else now. That whole area is changing so quickly that if we picked something today, we'd almost for sure have it wrong. So I think it's too early to know. So I think we're going to see an environment that you're going to see a lot of different definitions of this and a lot of different takes on what it means for that API. There are sort of favorites that happen in the industry today about RESTful API and everything's going to be XML and these kinds of things. And yeah, I mean that's maybe the basics, but sort of the model of the network, that is something that will evolve over a period of time. I do believe it is, and Dan could probably correct me on this, it is ultimately the charter of the ONF to address these northbound APIs, but it's sort of, let's get the heavy work out of the way of knowing what's going to go down on the sort of the southbound API first, and let the others settle out a little bit and work on the northbound. But I think a lot of people would agree with me that ultimately the real value is on the northbound. Yes.
So I have a question. In the newer this architecture, what is the requirement for reliability or availability of the switches? Earlier it used to be active or active standby.
Right.
But I don't see, maybe it's implicitly built that there is no standby shown here, or is it because of multipath the requirement has gone down for active amongst the switches?
So, that's one of the great advantages of the multi-rooted fat tree, is that it has a lot of reliability built into it. If I lose a spine, I lose 1 over n of my bandwidth, where n is the number of spines in that network. So how much reliability do you want? You can sort of dial your own, and customers have different requirements for those kinds of things. Before we had overlays and we're doing this sort of layer 3 multipathing across this network, even for the L2 traffic, we were stuck with the spanning tree. And the spanning tree, we went to a lot of work to get it to be 1+1 redundancy, the split spanning tree or virtual port channels and all these things. But that was really, really hard to do. It was a very unnatural thing to do. Here, I have 4-way. At the leaf, it depends, and that really goes customer by customer. Some people have their hosts are dual attached. Some people say my application has redundancy, and if I lose the host, I don't care. If you look at Google, or lose a rack, doesn't matter. I'll replace it tomorrow. That's great, fabulous redundancy. I like the model in general that says assume that there's a failure. Now, how do I work? Rather than assume that I'm going to eliminate failures. And I think traditionally we've been saying, I'm going to eliminate failures.
Right.
And moving forward, I think we're going to say, yeah, no, I'm assuming that it's failed. Now what happens?
Right. So
And
that's the acceptance you're seeing from the customer point of
acceptance, you know,
view. Okay.
I've been hiding away for a year and a half, but a year and a half ago, there's religion about high availability. Religion. There's, you know, there are people who aren't in the valley, aren't deeply ingrained in this industry that have a couple of rule of thumbs that they know and they live by, and it's worked for them for many years. And maybe when they were younger, they learned this was be the truth of things. And you come in and question that truth, and they say, no, no, no. Especially if they're in a position to say no to you.
Right.
So it'll take some time, but ultimately, I think what you'll see is you have fine-grained redundancy here, and we will see smaller switches, not bigger switches, in the future.
Got it. Okay, one related question, if I may. So now that instead of multiple hops, it is turned to only 2 hops at most. So does it mean that the latency or the delay in a switch requirement has gone a little bit relaxed, or is it just what are your views on that?
I was trying to think of a crude analogy about sex and money, but in latency, but the metrics go the wrong way. You can never have too little latency. And so, sure, the latency is going to be more predictable, lower in this kind of network. By the way, I mean, I do 2 because it's easy for PowerPoint, but you could easily see this as a 3-tier. Although I do think the 2-tier will be the dominant deployment. But you know, it doesn't mean that people say, "Oh, okay, well now you go ahead and jack the latency up again." No, lower latency is better across the board.
Okay, thanks.
I have a closing question. So you have launched a number of startups. Is it like a recipe for success? And what is that recipe? Before you say yes.
What is the recipe of success for these startups? Pragmatism. I reduce it to one word, and actually 2. Pragmatism and execution. You've got to figure out what you want to build. It's got to be pragmatic, something that can be done, something that's going to work well in the marketplace, has enough vision, but isn't too far out there, and then you have to execute. And the execute's the hard part. And actually, there's one more big piece of it. You need luck.
All right, thank you so much, Tom. Thank you.
All right, thank you.